Whether it's the design of a space exploration vehicle or a family home in the suburbs, insulating the structure is critically important. For space travel in particular, the insulating material must be lightweight, yet strong, which eliminates most traditional solutions. Luckily, researchers at NASA's Glenn Research Center are breaking new ground in aerogel technology that has the potential to radically change the way we approach this problem and impact the world.
Aerogels are a porous solid material. They're highly porous, can be as much as 98% porous. They were actually invented in the 30s by Professor Sam Kistler, who was just curious about whether he could remove liquid from a gel, which is basically a solid material that has a liquid in it, without collapsing the gel structure, so retaining it in the solid material. So he used a process called supercritical fluid extraction to remove alcohol from silica gel and actually several other types of gels, and created a structure. This is an example of a silica aerogel. It's a very interesting material in that the pore size of the silica aerogel is extremely small, and that's what makes it a really good insulating material. However, silica aerogels themselves are very brittle, so you can see that I very easily can break that. And so at NASA, we've been, for the last number of years, working on ways to take advantage of all of the good properties that aerogels have, being they have this high porosity, very small pore structure, but they're very delicate materials. So we want to take advantage of that by increasing the durability of those materials.
So what processes do you use in order to do that, to make them stronger materials?
We've started looking at primarily polymer structures for the aerogel. We're using a process that introduces liquid CO2 into the gel, replacing the solvent that's in there. Supercritical point for liquid CO2 is only 30-some degrees, so much safer process to make the aerogel these days. But we are still able to achieve 90% porosity in these polymer aerogels, and they are in fact even stronger than the silica polymer hybrids that we were making a few years ago.
You've mentioned the use of polymers in these. Can you explain a little bit what a polymer is and how it's different perhaps from other organic molecules?
Well, a polymer is a large organic molecule, and most people call polymers plastics. These are polymers are made up really of long chains of small molecules, all covalently bonded together. When we make an aerogel structure out of a polymer, we take those linear polymer chains and then we use something called a crosslinker to create a network structure. The network structure is what you need to get a gel.
So you've mentioned that these aerogels are very robust and that they're also very good insulators. So can you talk to us a little bit about some of the applications of these aerogels, perhaps commercially, as well as how they might be relevant to NASA?
Yeah, so for NASA, we're interested in insulation materials for many, many different applications. Cryotanks, for instance, which contain cryogenic fuels, you need to insulate those. Spacesuits, you need insulation. The particular project that we've been working on in the last few years is basically an aeroshell type of a structure that's used to slow down spacecraft or payloads to land on another planet. And in that regard, we've been making these aerogels now in a thin film form. So that's what this is. This actually is the same aerogel structure as that thicker part that I was just holding. But this making it thinner, just like aluminum foil is flexible, but an aluminum bar is not. This is a flexible form of the insulation. So this could be used to wrap around things, but it also can be used in this decelerator structure, this aeroshell that I was mentioning. These can basically blow up like a balloon, and the insulation has to be just as flexible as the rest of the structure.
So it seems like these would be great for all kinds of different applications, even in in someone's home to insulate refrigerators or things like that. Is there anything that's prohibitive from these being deployed, cost or anything else?
These would be, at least initially, more expensive than your conventional foam insulation. The advantage that the aerogels have, though, is the R value. So the insulation, and this is why NASA's interested, they're much better than conventional polymer foams or fiberglass that you would find in your home. This is about an inch thick, and that would probably provide about an R of 10, versus a polymer foam, which would probably have an R of 2 to 4. So you would need much thicker insulation for that. So you could reduce the thickness of the insulation. Where that would be used maybe is in a new refrigerator, where you could have better insulation in the walls without making the walls thicker. Where you would probably not see this used because of the expense would be, say, in your attic, where you might have enough room to put 12 inches of insulation. So you don't need this, so you could use the cheaper material.
So I've seen, you've already mentioned the deployment chute as one of the applications. I've also seen where aerogels have been discussed as being used for missions to Venus or something like that, where you would have very harsh conditions because of the atmosphere. Could you tell us a little bit about that?
Well, so this aerogel would not be one for Venus. We do have some other aerogels now being developed in our group that are made out of aluminosilicates, and these can withstand very high temperatures. Polyimide is going to be good up to about 300 degrees C, maybe a little higher if your application is an inflatable decelerator and it only lasts for 90 seconds. Mars in particular is different than where we've been before, which is the moon or in space, where you're really in a vacuum. And the only insulation you really need is radiative insulation. So what we use in spacesuits right now is something called multi-layer insulation, or MLI. And this is basically alternating layers of aluminized mylar, which have many, many layers of that, and each layer reflects the heat back. In a vacuum, that's all the insulation you need. When you have an atmosphere like Mars does, which is it's not as much of an atmosphere as Earth. It's actually kind of a light vacuum. You need insulation which provides more than just protection from radiative heat transfer. You have heat conduction through the solid or gas, and that's where an aerogel really has a lot of strength. This is the only material actually that meets requirements for insulating for Mars planetary surface missions, for spacesuits or rovers or things like that.
So what is the future of this work? What are you working on now to try and either find new applications or improve what you've already discovered?
We're starting to look at nanocomposite aerogels, where we're maybe taking carbon nanotubes inside of the polyimide aerogel as an added reinforcement. Also, other types of these types of nano reinforcements. And some of that is geared toward making the materials even stronger. Another avenue that we're looking at is different types of polymers. So we've made this polymer version of an aerogel. Can we make other polymers and also give them these types of porosity? Another thing that we're working on with the aerogels is taking advantage of other properties of this material. Besides being a great insulator, it's a very low dielectric material. So this material has a dielectric of about 1.15, which is approaching the dielectric constant of air. That's probably because it's about 90% air. And why that's important, we can use this to make as a substrate for antennas. So you print a pattern on here, and it can be an antenna which performs better than current ones. You can get wider bandwidths from a single antenna. It can operate with higher gain, and it's about 10 times lighter. So it's sort of a win-win-win situation where you get better performance in a couple different ways, and it has less weight. using this same flexible form, we could make conformable antennas. So, just another avenue.
So we are going to do a little demonstration to see the thermal properties of aerogels. Can you walk us through what we're going to do?
Sure. Well, I just have a beaker of water right now on a hot plate that's set at about 170 degrees C, and you can see that the water vapor is coming off of the beaker. And I'm going to remove that, and I'm going to put this piece of polyimide aerogel down on the hot plate. And even though if I put my hand directly on the hot plate without the aerogel, I would probably get burned pretty bad. Right now, I can put my hand firmly on the aerogel and I don't feel any heat coming through at all. You can do it too.
So the aerogel acts as an insulator and doesn't allow the heat from the hot plate to come up through to the hand.
Essentially, one side of that is at 170 degrees C, which is quite hot, but I can't pick up any, maybe about 30 degrees on this side.
I'm standing here with Stephanie Vivad at NASA's Glenn Research Center, and she's going to synthesize some aerogels for us. So Stephanie, can you walk us through what's going on?
Absolutely. I'm going to show you actually a couple of different types of aerogels, but what I have working right now is a polyimide aerogel. So far I've added the solvent that I use, which is N-methylpyrrolidinone, and I'm going to add, I've added the diamine. The dianhydride is coming up next. So what I'm basically making is a polyamic acid. So it's not yet a polyimide. It's got a couple of OH groups on it, so it's going to stir for a little bit. While that's stirring, I'm going to dissolve the dianhydride in there. And in the meantime, I take the chains that I make the polyamic acid and I cross-link it with triamine. And the triamine that I'm using...
So basically you're making the polymer structures and now you're going to link the polymers together.
Correct. Exactly. And so basically what we'll do is a triamine will react with an acetic anhydride, and basically we will end cap the polymer structure with an dianhydride, and then we'll be able to react with an amine. We've decided to do chemical imidization, and what that allows us to do is operate at room temperatures, which is, for industry's sake, more cost efficient and safer, obviously. So I'm going to add my cross-linker. And so that'll start to get quite a bit more viscous, and it's going to release a little water, and you can see already it starts to get viscous immediately. And okay, we've got a little bit of exotherm going on. So that's stirring. The acetic anhydride and pyridine basically act as a water scavenger and a base catalyst. So I'm going to add that. And so once I pour this also, it's going to sit for 24 hours. I'm just going to pour this. It's pretty viscous. What we do then is we use these molds, which I'll show you in a second why they seem to be so handy. So I had poured these not too long ago, and these have already gelled. So what I will show you, if it makes it easier, the process is once this gels, and it gels fairly quickly, within maybe 15 minutes, there'll be a little bit of residue left, and then we just basically extract it. Now it's pretty sturdy, so you can really handle that. So now what you have is a gel, and we don't leave that out. We will take the solvent that it's made in, and we'll transfer it into that solvent, and we'll keep it in there. And then what happens is we go through a series of swapping this high boiling point solvent out with acetone. And that makes it, again, a little more environmentally friendly, easier to remove, and we take it through a process of supercritical fluid extraction at that point to make the aerogel.
Is this something that a high school or college chemistry student could do in a chemistry lab?
Oh, absolutely, absolutely. You know, the monomers that we use and the solvents are are pretty common in any laboratory. That there's nothing that is so dangerous that you would or even so expensive that a school or university wouldn't purchase. The issue would be to create the aerogel by supercritical fluid extraction, and that is where you need a specific system because of the fact that you're going to such high pressures and temperatures that you really need a specially designed system. And I know that you can buy benchtop systems. A lot of schools can find smaller, more economical systems. We do a large volume, so we have a fairly large system. But I also know that there's been different school projects, like science projects that people have done, where they've made starch aerogels at home in their freezer through sublimation. So there's a lot of different things you can do. But absolutely, this is something I'd encourage anybody to get to learn how to do this.
The techniques and technologies being developed here in the aerogel lab at NASA's Glenn Research Center has the potential to impact a broad range of industries, and we are only now beginning to scratch the surface of what is possible. Join us next time as we travel to the Ballistic Impact Lab and see how NASA scientists are working to make air and space travel safer, all on tomorrow's discoveries.